Imagine this for a second. You've ordered something custom, maybe complex, and instead of a human factory worker, you see this nimble, AI-driven robotic arm. It's meticulously assembling these intricate parts with just incredible precision, and it's making real-time adjustments based on, subtle sensor feedback.
Or picture this. Maybe you're recovering from surgery. And instead of only human nurses, there's also a gentle, intelligent robot assistant. It helps with your medication, checks your vitals, maybe even offers a bit of a comforting presence. It could really ease the load on the human staff.
Exactly. And these scenarios, they aren't just like concepts anymore, are they? This is becoming our reality. It's driven by this really powerful synergy. Okay, so let's unpack this a bit. Today, we're taking a deep dive into a topic that's really jumped off the pages of science fiction. It's a vibrant, transformative force shaping our world right now. We're talking about the profound synergy between artificial intelligence and robotics.
It's a field just brimming with innovation. It's actively reshaping, well, almost everything. How we work, how we get healthcare, even, how we explore space. And our mission today, really, is to cut through all the noise. There's just so much information swirling around. We want to give you a kind of shortcut to being truly well-informed on this.
Right.
We've pulled together insights from a whole stack of sources. We've got rigorous academic reviews, in-depth industry analyses, cutting-edge research papers just published, and even some pretty surprising, thought-provoking news stories that really highlight the real-world impact.
So the goal is?
The goal is to distill the most important bits of knowledge, the key insights. We want to highlight surprising facts, crucial connections, basically help you understand what's most vital in this incredibly dynamic landscape.
And it really is dynamic. We're going to journey through the history. First, it's surprisingly deep, actually, the history of machine intelligence. See how these mechanical marvels and digital brains first took shape?
Then we'll dive into the groundbreaking applications, how they're transforming whole industries globally, manufacturing floors, operating rooms, you name it.
We'll also need to confront the big challenges, right?
Yeah.
Both the technical hurdles and the ethical questions that researchers and engineers are really grappling with right now.
Absolutely. And finally, we'll look ahead. Cast our gaze towards those, mind-bending future possibilities. Things that stretch the limits of how we even define intelligence.
And what it means to be human in a world that's becoming more and more automated. So, let's start by laying down some foundations. We need to understand the basics first.
Definitely. To really appreciate this convergence, the synergy we're talking about, and why there's so much excitement, it helps to understand each field on its own first. Think of it like understanding the body and the mind separately before you see how they work together.
Okay, body and mind. I like that. Let's start with the body then. Robotics, the physical side of things.
Right. Robotics, it's a really multidisciplinary field. It covers everything. The design, the construction, the operation, and ultimately the use of robots. At its heart, it's the engineering discipline focused on building machines that perform physical tasks out there in the real world.
So its core purpose is efficiency, safety, automation.
All of the above. Fundamentally, it revolves around using technology to streamline processes, enhance efficiency, improve safety, all through automation. It's about taking those jobs that are maybe too dangerous, too dirty, or just mind-numbingly dull for humans and letting machines handle them.
Makes sense. And historically, that's where we've seen them most.
Yeah.
In those arduous, hazardous, or super repetitive roles.
Exactly. Think about lifting heavy machinery on a car assembly line, or welding with incredible precision over and over, or the meticulous work in electronics assembly.
Right. Tasks where consistency is key.
Precisely. And that's the key advantage. Unlike a human worker who gets tired or bored, or maybe just loses focus, which can lead to errors or slowdowns, a robot will just execute the same activity consistently, with the same effectiveness, the same accuracy, day in, day out.
No coffee breaks needed.
No coffee breaks, no burnout. That relentless, precise performance, it's a massive driver for efficiency and quality, especially in industrial settings.
Okay, so that's the body robotics. Now let's talk about the mind. Artificial intelligence, AI, this is the part that gives the robot its spark, its intelligence.
Right. In AI, as you know, it's a huge field. But for our purposes today, we're focusing on the AI that enables robots to think, in a sense. At its most basic, AI is the capability of machines to mimic human intelligence.
Mimic human intelligence. What does that actually involve?
It covers a whole range of cognitive tasks, things like learning from experience, understanding language, recognizing complex patterns in images, data, sound, and critically, making decisions. Sophisticated, data-driven decisions that can adapt when things change. It's the thinking, the learning part of the equation.
And machine learning, ML, that fits in here how it seems to be everywhere now.
It's absolutely central, especially in recent years. ML is a core component of AI where algorithms aren't just following instructions. They're designed to identify intricate patterns within huge amounts of data. And the crucial part is they improve their performance over time without being explicitly programmed for every single possibility. They learn on their own.
How do they learn? Just by looking at data.
Essentially, yes. By analyzing examples, finding correlations, and getting feedback, whether that feedback is explicit, like being told that was wrong, or implicit, like achieving a goal or not.
No.
One of our sources used a great analogy. Think of AI neural networks, which are key to ML, as being like the complex adaptive networks in a biological brain. And robotics, then, is like the anatomical structure of the human body, the physical form that carries out the brain's commands.
Mind and body. It clicks now. A very useful analogy.
It really is. And it helps explain that other critical aspect of AI in robotics, autonomous operation.
Meaning they don't need constant human control.
Exactly. AI systems aren't just following a fixed script. They can acquire new knowledge, continuously adjust their behavior independently. They don't need step-by-step instructions all the time. They learn, adapt, make decisions on the fly based on what they perceive from their environment.
Okay, so we have the body robotics and the mind AI, especially
Right.
ML. Where does the magic happen? The synergy.
That's machine intelligence, or MI. This is the powerful intersection, the aha moment, if you like. It's when you embed those sophisticated machine learning algorithms directly into the robotic systems, deeply integrate them.
And that integration allows.
It allows the robots not just to perceive their environment through sensors, but to make real-time decisions, instantly, and dynamically adjust their actions based on the feedback they're getting right then and there.
So they're not just pre-programmed tools anymore. They're intelligent actors.
That's a great way to put it. It's a fundamental shift. Traditional robotics often relied on those rigid, pre-programmed instructions. The robot did exactly what it was told, usually in a very controlled, unchanging setting.
Right, like on an assembly line where everything is always in the same place.
Precisely. But AI-enabled robots, they can learn from new data, they can respond intelligently to unexpected changes, an obstacle appears, a part is slightly different, and they can even collaborate more naturally, more intuitively with humans.
So the robot arm that used to be behind a cage,
Mhm.
now it can potentially work right next to a person, understanding and adapting.
That's the direction things are moving. And the overarching goal of this whole field, this machine intelligence field, which is still pretty nascent but evolving incredibly fast, is to develop reliable, embodiment-aware AI systems.
Embodiment aware. What does that mean exactly?
It means the AI doesn't just think in the abstract. It has a form of self-awareness about its own physical body, its capabilities, its limitations, and it has a deep, nuanced understanding of its physical environment. This allows it to dynamically adapt its behavior based on the body it's operating and the real-world conditions it encounters.
So the AI knows it's controlling this specific arm with these specific sensors in this specific room.
Essentially, yes, that awareness is key. It promises to fundamentally transform not just how we use robots, but how we engage with them. Less like tools, more like intelligent, adaptive partners.
Building a truly symbiotic relationship, the AI's brain power and the robot's physical form, constantly informing and improving each other.
You've got it. That's the core idea of machine intelligence.
Okay, that clarifies the what and the why. Now let's rewind a bit. You mentioned this history stretches back further than people might think. How far back are we talking?
Well, conceptually, the fascination with creating artificial life or intelligent machines, our sources trace that impulse back centuries, even to the 12th century, with early designs for automata, mechanical figures. The desire isn't new.
Right, the old legends of golems and clockwork creations. But in terms of actual functioning robots,
Looking at the more recent pioneering systems that really started to resemble what we think of as robots today, we see some key milestones. A big one was in 1973. A research team at Japan's Waseda University introduced the Wabot-1.
Wabot 1, what was special about it?
It was groundbreaking because it was the first full-scale humanoid robot designed specifically to replicate human motion. Now, it was rudimentary by today's standards.
How rudimentary.
And it could take a few steps, grasp objects with pretty primitive hands, even communicate a bit in Japanese, but it laid the blueprint. The first real attempt at human-like movement and object manipulation in one self-contained system.
Fascinating. And then came PMA.
Yes, in 1978. Unimation, a real pioneer in robotics, introduced the Programmable Universal Machine for Assembly PUMA. This was a big leap forward technologically.
How so?
Unlike earlier industrial robots, PUMA had 6 degrees of freedom. That gave it unprecedented dexterity, much more flexibility for complex assembly tasks. It really took off. It became a standard reference in both industry and academia for what they called anthropomorphic robots, human-like in form and movement. Its design really influenced industrial automation for decades. It basically wrote the manual for mechanizing complex, repetitive factory work.
So the late 70s set the stage for industrial automation. What about the AI side? When did that really start merging with robotics in a meaningful way?
The 1980s were absolutely pivotal, particularly with the rise of reinforcement learning, RL, this discipline, which is a cornerstone of modern AI now. It actually emerged by integrating ideas from different fields. Surprisingly, some initial concepts came from 18th century psychological research on animal behavior.
Animal behavior.
Mm.
How does that connect to robots?
Specifically, the idea of trial and error learning. Think Pavlov's dogs, Skinner's boxes. How organisms learn optimal behaviors by interacting with their environment and getting rewards or punishments.
Okay. So applying that reward-punishment idea to machines.
Exactly. The core mechanism in RL is that a specific behavior pattern emerges because the machine interacts with its environment. It tries things out. It observes the consequences, gets a positive reward signal if it does something good towards its goal, a negative one if it does something bad. Through this iterative process, it learns which actions lead to better outcomes.
And it remembers those effective patterns.
Right. They persist and get refined over time, even after the initial stimuli are gone. It learns by doing and experiencing the results.
Were there early examples of this actually working?
Definitely. Arthur Samuel, way back in 1959, demonstrated this with his checkers playing program. It adjusted its strategy based on the anticipated reward of different board positions, a kind of early temporal difference learning.
So the program learned to play checkers better over time.
Yes, it improved significantly over thousands of games, learning from its own experience without being explicitly programmed with every single strategy. Then, moving into the 80s, in 1983, we saw the actor-critic architecture, a more advanced RL technique used to tackle the classic control problem of pole balancing.
Like trying to balance a broomstick on your head.
Exactly that kind of problem. It requires constant real-time adjustments based on feedback. Then, a huge milestone in 1989. Chris Watkin pioneered the Q-learning algorithm.
Q-learning. Why was that a game changer?
Because it fully integrated ideas from optimal control theory with online learning. It provided a solid mathematical framework for a robot to learn the Q value of taking any possible action in any given situation purely through trial and error.
So it could figure out the best move even in complex, uncertain situations.
Precisely. By continuously updating these Q values based on the rewards it received. It's fundamental to how many modern robots learn complex tasks without a human constantly telling them what to do.
Okay, so RL provided a way for robots to learn. What about controlling their physical movements more effectively, especially around humans?
That was another key area of progress in the mid-80s and 90s. Moving beyond just rigid, pre-planned motions, John J. Craig and Mark Rabert introduced a new hybrid control technique. It allowed robot manipulators to simultaneously control both their position and the force they applied.
Why is controlling both important?
Think about tasks that need compliance. Like inserting a peg into a hole, you need to control the position precisely, but also apply force gently so you don't jam it. Or a robot interacting with a person. This hybrid control made those kinds of compliant motions possible.
And speaking of interacting with people, safety must have become a bigger concern.
Absolutely. And that's where Neville Hogan's work in the mid-80s on impedance control was crucial. It's fundamental to the safe human-robot collaboration we see today with cobots.
Impedance control, does that mean the robot can sort of feel and react to contact?
In essence, yes. It allows the robot to behave like it has a certain mechanical impedance, like a spring or damper, so it can yield or react appropriately and safely if it bumps into something or someone. It's a core safety feature for robots working outside cages.
Got it. What about moving around obstacles?
Another big step came in 1986 from Usama Khatib. His work on real-time obstacle avoidance using artificial potential fields was seminal.
artificial potential fields, like invisible force field.
Kind of. The idea is you model obstacles as repulsive forces, and the goal as an attractive force. The robot then navigates this potential field to find a path that avoids the obstacles while moving towards the goal. It enabled robots to operate dynamically in environments that weren't perfectly predictable.
And Khedive also developed the operational space framework.
Yes, in 1987, that was a major theoretical advance. It unified motion and force control into a single framework. Instead of thinking about controlling each individual joint of the robot, it focused on controlling the robot's end effector, the hand or tool, directly in the space where the task is being performed. This made programming and controlling complex movements much more intuitive.
So by the 90s, the theoretical foundations for smarter, safer, more adaptable robots were really falling into place. Did we start seeing more ambitious projects then?
We certainly did. The vision for humanoids and autonomous vehicles really started to gain traction. Honda began its serious humanoid research in the early 90s with the P1 prototype.
P1. Was it like Asimo?
It was a precursor, much larger though, almost 2 meters tall, 175 kilos. It could walk, but not very fast, maybe 2 kilometers. And the battery life was limited, like 15 minutes.
Wow. Still a huge undertaking back then.
Yeah, immense. It was a really significant early step, paving the way for more agile humanoids later on.
And telerobotics. Controlling robots remotely.
A major breakthrough there was the 1993 Robotics mission. A German team led by Gerd Herzinger successfully demonstrated the first space robot operated directly from Earth, controlling it precisely over those vast distances.
Controlling a robot in space from Earth in 93? That's impressive.
It was a real feat of engineering, remote control, real-time feedback, robust design for space. Proved complex tasks could be done remotely in hazardous environments.
And autonomous driving. We hear so much about it now, but when did it really start showing promise?
There was remarkable progress in the mid-90s. In 1995, Ernst Dickmanns and his team in Germany, part of the Prometheus project, they had a modified Mercedes S-Class drive autonomously for about 95% of a nearly 1,800-kilometer trip, from Munich to Odense in Denmark.
Wait, 1,800 kilometers in 1995, mostly autonomous?
Yep. It wasn't just a lab demo, it was a serious road test handling real roads, real traffic at high speeds, showcased pretty advanced vision and control systems for the time.
Incredible. And of course, the 90s also gave us Deep Blue.
Ah, yes, IBM's Deep Blue, the chess-playing computer. It famously defeated the reigning world chess champion Garry Kasparov, first in a single game in 96, then the full match in 97.
Now, a human still made the physical moves, right?
Yeah.
But the decisions were the AI's.
Correct. But Deep Blue's victory was this stunning demonstration of AI's raw computational power. It proved machines could master tasks previously thought to require unique human genius. It really forced a rethink about what intelligence means.
So all these breakthroughs in learning, control, vision, computation, they laid the groundwork for what we see today.
Absolutely. Building on all that, the turn of the century saw more progress in autonomous navigation. That work underpinned the simultaneous localization and mapping algorithms, SLAM, that are so crucial now.
SLAM. That's how a robot figures out where it is while building a map of a new place.
Exactly. It lets a robot navigate an unknown environment. It's fundamental for autonomous cars, drones, vacuum cleaners, you name it. And we saw early practical applications too. Like in 1998, Wolfram Burgard's team built an autonomous tour guide robot for a museum in Bonn. It used these principles to navigate and interact with people in a complex public space.
Okay, so that brings us pretty much up to date on the journey. Now, let's peel back the layers on how AI is actually empowering robots today. The technical deep dive.
Right. Let's get into the core technologies acting as the robot's brain and senses.
Where do we start? Machine learning again.
Definitely. ML is the brain. It allows robots to move beyond that rigid programming. It lets them acquire and execute tasks by, say, monitoring and imitating human actions, or by learning patterns from massive data sets.
So it's not just theory, it has real impact.
Huge impact, enhancing intelligence, adaptability everywhere. Think of an industrial robot learning the best way to handle delicate electronics by watching an expert human.
Or my robot vacuum learning the layout of my messy living room.
Exactly. It maps your home, learns to avoid obstacles, gets more efficient over time. It learns without you explicitly reprogramming it for every new piece of furniture. ML makes machines dynamic learners.
Okay, learning is one thing, but robots need to perceive the world too, right? How does AI give them sight?
Through computer vision, this is absolutely transformative. It allows robots to effectively see and interpret their surroundings. recognize objects, identify important features, understand the scene, and based on that visual understanding, they can make appropriate responses.
So they're not just blindly executing tasks anymore.
Precisely. They move from being mere executors of repetitive duties to becoming. One source called them cognitive collaborators, machines that perceive, understand, and act based on that understanding.
How does the tech work? How do they understand images?
Often, the core technology involves convolutional neural networks, or CNNs. These are inspired by the human visual cortex. CNNs don't just see raw pixels, they learn to identify hierarchies of features. Simple things first, like edges and corners. Then they combine those into more complex shapes. And finally, they assemble those shapes into recognizable objects.
So it's layered understanding.
Yes. It allows robots to go beyond just detecting that an object is there, to understanding what it is and what its context is. Navigating a street means distinguishing pedestrians from signs. Inspecting a circuit board means spotting tiny defects. Recognizing human gestures means understanding commands.
That sounds incredibly data-intensive, processing all that visual information in real time.
It is, and speed is critical. Which brings us to edge computing.
Edge computing, meaning processing happens on the robot.
Or very close to it. At the edge of the network, robots generate huge, continuous streams of data from sensors, cameras, LiDAR, touch sensors. Instead of sending all that data back to a remote cloud server for processing, edge computing allows it to be analyzed promptly, right there near the robot.
What's the advantage of that?
Latency, speed. It dramatically reduces delays, you get real-time awareness. Robots can make judgments and take actions much, much faster, often in milliseconds.
And in some situations, milliseconds matter. A lot.
Absolutely. Think of an autonomous car needing to brake instantly, or a surgical robot needing immediate feedback. That speed advantage from edge computing can be crucial for safety and performance.
Okay, so they have brains, ML, sight, CV, and fast local processing, edge. What about other senses? Do robots just see?
No. Just like humans, they benefit from multiple senses. AI leverages diverse sensory inputs to help robots acquire more nuanced, task-specific skills.
What kinds of sensors are we talking about?
Our sources list quite a few. There are time-of-flight optical sensors that use light, like lasers, to measure distance very precisely. Temperature and humidity sensors for environmental awareness. Ultrasonic sensors using sound waves like sonar, great for detecting objects up close or in poor visibility. Vibration sensors, which can detect wear and tear for predictive maintenance.
Predictive maintenance. That's clever.
It is. And then there are millimeter wave sensors. They operate at specific radio frequencies and can actually see through things like fog, dust, or heavy rain where cameras might struggle.
So each sensor offers a different kind of information, a different superpower.
Exactly. And the real power comes when AI fuses the data from multiple sensors. It creates a richer, more robust understanding of the world, a multimodal perception.
Like building up common sense from different inputs.
Kind of. It dramatically enhances their cognitive capabilities, allows them to respond more effectively and adapt to a much wider range of dynamic, unpredictable situations. They overcome the limitations of relying on just one sense.
And all this AI and sensing capability has to work with the physical robot parts, right? The motors, the arms.
Absolutely. One source provides a nice diagram showing the key physical components. You've got motors, piezo motors, electric motors providing the drive. Actuators are like the muscles, converting energy into motion. You have all the sensors we just discussed gathering input. Then things like muscle wires or pneumatic air muscles, which can offer more fluid, human-like movements for delicate tasks. And of course, a power supply.
And the AI connects all of this.
It's deeply integrated. The AI receives the sensory data, processes it using ML, makes decisions, and then sends commands back to the actuators to produce intelligent, complex behaviors. It's the system that truly brings the brain and body together, making the whole thing work cohesively.
Okay, that technical dive was really helpful. Now let's zoom out. Where is this powerful combination of AI and robotics actually making a difference? What are the big application areas?
The impact is already huge and growing fast across so many sectors. Manufacturing and industrial automation is maybe the most established, but it's still being transformed.
How so? Beyond just faster assembly?
Yes. We're seeing enhanced production volume, sure, but also drastically increased efficiency from fewer errors. Much higher safety by taking humans out of dangerous spots. And greater adaptability in production lines. AI is particularly valuable in complex assembly, like in aerospace. The tolerances are incredibly tight. AI-powered vision systems allow robots to make real-time adjustments, autonomously figure out the best path for a task, even as they're doing it.
Less waste, more precision.
Exactly. And it goes beyond assembly. Think packaging and logistics. AI robots are optimizing the whole flow. They learn the most efficient ways to pack items, simplify equipment setup and movement. We're seeing advanced quality control, too. AI vision spotting microscopic flaws humans could never see. And predictive maintenance analyzing sensor data to predict when a robot needs servicing before it breaks down.
Minimizing downtime, that's huge for factories.
Massive. And then there's warehouse automation. Companies like Amazon rely heavily on AI-guided robots for sorting, picking, transporting goods. It makes fulfillment incredibly fast and accurate.
Okay, manufacturing is a big one. What about healthcare? You mentioned that earlier.
Healthcare is undergoing a truly transformative era because of this. It's enhancing patient care, streamlining complex processes, and really augmenting what doctors and nurses can do.
Augmenting, not replacing.
That's the main focus, yes. For example, robotic surgical systems, like the Da Vinci system, they use AI for incredible precision in complex, minimally invasive surgeries. The robot's stability and dexterity allow surgeons to perform maneuvers impossible for the human hand alone. That often means faster recovery, better outcomes for patients.
What about after surgery? Rehabilitation.
That's another area. Rehabilitation robots with AI can adapt therapy based on the patient's actual performance in real time. Imagine a robot guiding a stroke patient's arm, learning how the muscles respond, and adjusting the exercise intensity automatically. Highly personalized treatment.
It sounds incredibly promising. You also mentioned robotic nursing.
There's definitely potential emerging there. The aim is to reduce the heavy workload on human nurses. These robots could potentially monitor patient vitals 24/7, assist with medication delivery, help patients with cognitive issues or disabilities with daily tasks, even providing companionship for the elderly, which is a growing need globally.
We saw robots step up during the pandemic too, didn't we?
We absolutely did. They played a critical role, screening patients, collecting samples, disinfecting hospitals, delivering supplies to infected patients, all reducing human exposure to the virus. And behind the scenes, AI was crucial in accelerating vaccine discovery, analyzing biological data at incredible speeds.
But it's not all smooth sailing, right? What do healthcare professionals think?
It's nuanced. One study we looked at involving Chinese nurses showed high expectations for robots reducing their workload, but they also had concerns.
Concerns like,
Worries about technological limitations potentially compromising patient safety, or losing that crucial human touch and care. They emphasize needing systems that are user-friendly, intelligent, humanized, and absolutely secure.
so the technology needs to be designed with the human element firmly in mind. It has to fit the workflow and the needs of both patients and staff.
Precisely. Practical application, human-centered design, just as important as the tech itself.
Makes sense. Okay, beyond healthcare, agriculture.
Hmm.
How are robots changing farming?
Through precision farming, AI-powered robots, often drones or autonomous tractors, equipped with advanced sensors. They can monitor crop health field by field, plant by plant almost. They can identify specific weeds or diseased plants, then precisely apply fertilizer or pesticide only where needed. Some can even harvest delicate crops, like strawberries, using vision to judge ripeness.
So much more targeted than traditional methods.
Much more. It leads to way more efficient resource use, less water, less chemical runoff, higher yields, less environmental impact. Systems like PathoBot for autonomous disease detection are examples of this already happening.
Logistics and supply chains seem like another natural fit.
Definitely. We touched on warehouses, but AI optimizes the whole chain. Robots guided by ML for sorting, packing, transport, AI algorithms optimizing delivery routes, predicting demand surges, dynamically managing inventory. It makes the entire system more agile, responsive, cost-effective, faster deliveries, happier customers.
And customer service.
Yeah.
We interact with AI there all the time now.
We do. AI-powered chatbots are everywhere. They handle a lot of the simpler, repetitive inquiries automatically, 247, and they learn from every interaction, getting better over time.
Freeing up human agents for the complex stuff.
Exactly. And we'll likely see them used even more in online and physical settings, taking on more sophisticated tasks.
What about robots in our daily lives? At home?
They're becoming more common. Robot vacuums, lawnmowers, these increasingly use AI to map spaces, adapt to changes, learn user habits, operate more intelligently than just following a simple pattern.
And more complex mobile robots, like ones that can move around freely.
That history goes back too. The shaky robot from the late 60s was a pioneer in mobile AI, learning to navigate and plan. Today, we have incredibly advanced systems like Roland Juster from the German Aerospace Center, designed for safe, dexterous interaction with humans.
But we don't see robots like Roland Justin walking down the street yet. Why not?
Cost is a major factor, and ensuring absolute safety and robustness for widespread daily use in complex, unstructured environments like our homes and cities, that's still a significant challenge they're working on.
What about flying robots? Drones?
UAVs have seen huge advancements, driven by smaller components, lower costs, better sensors, faster processing. They can stay airborne longer, operate more autonomously. They can use multiple cameras for real-time 3D mapping, complex motion planning, even tracking people for search and rescue.
But they have limitations too.
Flight time is still a challenge, often limited by battery weight. And ensuring safe interaction, especially as more drones occupy urban airspace, is a major focus for research and regulation.
And semi-autonomous cars are probably the most visible example for many people.
For sure. Features like adaptive cruise control, lane keeping, emergency braking, they all rely heavily on AI interpreting data from cameras, radar, LiDAR, making real-time decisions. The whole push towards fully autonomous driving is fundamentally an AI and robotics challenge.
Even finance is being transformed. That seems less obvious.
Oh, absolutely. AI is having a massive impact there, increasing efficiency, enhancing security, improving accessibility. Think fraud detection AI algorithms spotting anomalous transactions in milliseconds, far faster than humans. More accurate credit scoring models, personalized wealth management advice, high-speed algorithmic trading executing millions of trades.
It's the data processing speed.
That's key. AI can process vast amounts of financial data incredibly quickly, identify subtle patterns, predict market trends, tailor solutions. It even helps with compliance. AI can read and interpret complex regulatory changes, help update internal policies, provide quick data insights for reporting, faster, more transparent, lower-cost compliance. It's changing how finance works from the inside out.
Wow. Okay, one more frontier. Space exploration. How are AI and robotics helping us reach for the stars?
In several crucial ways. One is crew autonomy. AI enables astronauts to operate spacecraft and experiments with less minute-by-minute guidance from mission control.
Which is essential for long trips, like to Mars, where there are communication delays.
Exactly. Makes missions more self-sufficient. Then there's vehicle system management. AI basically turns the spacecraft itself into a robot. It can manage its own systems, diagnostics, navigation, especially when astronauts are busy or asleep.
Reduces astronaut workload.
Significantly. And finally, you have AI-enabled autonomous robots acting as crew assistants or proxies, monitoring systems, planning maneuvers, running experiments, even doing repairs in dangerous environments. Less risk for humans, more efficient missions.
So AI and robotics are crucial for the future of space exploration.
Absolutely fundamental, pushing the boundaries of what's possible out there.
Okay, so we've seen the applications are incredibly broad. Let's shift focus now to the human side of this, the human-machine frontier. How is this impacting jobs, collaboration, interaction?
This is where it gets really interesting and sometimes contentious. There's obviously concern about AI and robotics displacing human workers.
It's a common fear, right? Robots taking our jobs.
It is, but the picture our sources paint is more nuanced. The World Economic Forum, for instance, actually forecasted a net increase of about 12 million jobs globally by 2025, specifically because of this technological shift.
A net increase. How does that work?
It suggests that while some jobs involving repetitive tasks might be automated, new roles are being created in areas like robot design, maintenance, programming, AI training, data analysis, and managing these automated systems. So it frames it more as an opportunity, a need for workforce retraining, acquiring new skills. Humans can shift focus from the monotonous tasks to more intricate, creative, human-centric work.
So work changes, it doesn't necessarily disappear.
That seems to be the trend. AI and robotics automate the repetitive stuff, yes, but they also introduce adaptability and cognitive capabilities into roles that were previously just rote. We move from doing the work to managing and collaborating with the intelligent machines that augment our own abilities.
And a key human role in this new world is the robotics engineer. What does their job actually involve? It sounds complex.
It's incredibly diverse. Day to day, they could be installing robots, diagnosing complex faults, doing repairs, performing predictive maintenance based on sensor data. They need deep technical understanding, but also need to integrate that with operational needs. They identify data sources for AI training, work with other teams, ensure software meets user needs.
It's not just coding then.
Far from it. They might even be involved in establishing AI governance frameworks, the ethical guidelines, assessing conversational AI integrations, and critically staying on top of constantly evolving safety standards and international regulations for autonomous systems.
What kind of background do they need?
Typically, at least a bachelor's, often a master's, in fields like computer or electrical engineering, computer science. Strong programming skills, Python, C++, MATLAB are common, algorithm design, debugging. But beyond the technical skills, best engineers in this field are perpetual learners. They have strong problem-solving abilities and a real commitment to continuous improvement because the tech landscape changes so fast.
A demanding but crucial role. Now, what about robots working with humans? You mentioned cobots earlier.
Yes, collaborative robots, or cobots. This is a fundamental shift. Traditional industrial robots, big, powerful, fast, kept behind safety fences for good reason.
Because they could be dangerous if a human got too close.
Exactly. Cobots are designed differently. They're specifically intended for close physical interaction with humans, working side by side in a shared space.
How do they manage that safely?
Through multiple layers of safety mechanisms. Highly sensitive force and proximity sensors are key. They can detect if they bump into someone or if someone enters their immediate workspace, and they can slow down or stop instantly. They also have carefully programmed safety zones and speed limits. This allows tasks to be flexibly divided. Maybe the cobot does the heavy lifting or repetitive parts while the human does the final assembly or quality check. Ideal for things like low volume, high mix manufacturing.
Are there specific examples of these advanced cobots?
Yeah, systems like the Barrett Wham arm, the DLR lightweight robots, KUK's Iowa, and one source highlights Franca Emica's Panda system, which really focuses on human-centered design. These systems offer high precision, delicate manipulation capabilities, and importantly, compliance they can yield safely to external forces.
And they're easier to program.
Often, yes. Many allow for intuitive programming, like you can physically guide the robot arm through the motions you want it to learn, or just tap it to make it stop. Much easier than writing complex code for simple tasks.
So it lowers the barrier to using robots.
Significantly. There's often a two-tier approach. Specialists provide the core functions, but end users can assemble solutions more easily. Combine that with cloud platforms for sharing skills and updates. It's really expanding who can use robotics. This accessibility is expected to help integrate robots more seamlessly into our everyday lives, not just factories, but maybe hospitals, labs, even homes.
And as robots get closer, interacting more delicately, touch becomes important.
Vitally important. That leads us to tactile robotics, or haptic robots. These are designed to interact with and perceive objects through touch.
Using sensors on their grippers, like artificial skin.
Exactly. Pressure sensors, force sensors, they can detect texture, softness, temperature. This is crucial for delicate manipulation, picking up that fragile egg without breaking it. And it's fundamental for increasing safe, close, physical interaction between humans and robots. No need for barriers if the robot can feel and react gently. Tactile feedback enables tasks like assisting surgery, handling soft fruit, providing physical therapy. It makes interactions far more sophisticated.
Okay, the potential is clearly enormous, but we need to talk about the challenges too. It's not all straightforward progress. There are technical roadblocks and some pretty deep ethical questions.
Absolutely. On the technical side, one major hurdle is data. High-quality data and lots of it.
For training the machine learning models.
Yes. These advanced robots need massive amounts of diverse, well-labeled data to learn effectively. Collecting that data in robotics is often time-consuming, expensive, and sometimes risky. Think about gathering data on countless ways to grasp different objects or thousands of hours of human-robot interaction. You either collect it manually, which is slow, or you use simulations.
But simulations aren't perfect, right? The sim-to-real gap.
Exactly. What works perfectly in a clean simulation doesn't always translate flawlessly to the messy, unpredictable real world. Bridging that gap is a persistent challenge.
What about speed and reliability?
Critical issues. Unlike, say, recommending a movie where a few seconds delay isn't a disaster, robots often need to react in milliseconds. Ensuring ML models run fast enough and remain stable in dynamic environments where lighting changes, things move unexpectedly, sensors get noisy, that's a much harder problem than for purely software AI.
The real world is messy.
Very messy. And the AI needs to handle that robustly, which leads directly to safety and reliability concerns.
The nightmare scenario. A robot making a bad decision based on flawed data or a poorly trained model.
That's the core worry. Especially in high-stakes areas, healthcare, transport, critical infrastructure, a mistake could have serious consequences. So we desperately need robust standards, rigorous testing methods that go beyond typical software checks, and foolproof fail-safe mechanisms. Public trust hinges entirely on these systems being absolutely reliable, even when the unexpected happens.
And underlying all this is that gap you mentioned between the algorithm and the physical world.
Yes, what one source called the significant disparity between the algorithmic realm and the physical realm. It hinders creating truly intelligent, user-friendly robots that can handle our complex, human-centric world with dexterity and common sense. It's one thing for AI to master Go. It's another for a robot to reliably pour a glass of water without spilling, given all the variations in glasses, surfaces, liquid levels. Bridging that gap between clean code and messy reality is central to progress.
Okay, those are significant technical hurdles. Now let's get into the ethical and societal dilemmas. You said earlier, here's where it gets really interesting.
It really does, because the rapid adoption of AI, not just in robotics but across sectors like finance, raises profound ethical questions. These aren't just technical bugs to fix, they're fundamental societal challenges.
Like bias in AI models.
That's a major one. If the data used to train AI reflects historical societal biases in lending, hiring, policing, the AI can inadvertently learn and even amplify those biases, making discriminatory decisions automatically at scale. This means organizations must implement responsible AI practices, auditing for fairness, ensuring transparency, actively working to mitigate bias. It's not optional, it's essential to avoid worsening inequalities.
And data privacy and security.
Yeah.
With all the data these systems collect.
Absolutely critical. These systems handle sensitive personal, financial, medical data. We need robust security, clear policies on data use, anonymity where needed, and transparency in how AI makes decisions that affect people's lives.
People need to know how decisions are made about them.
Yeah.
And be able to challenge them.
Yes, especially when the decision-making involves complex black box AI models that even the creators might not fully understand.
And then there's the accountability question. As robots get more autonomous, who's responsible when something goes wrong?
That's a huge unresolved legal and ethical debate. If an autonomous car has an accident, is it the manufacturer, the software programmer, the owner, the AI itself? We don't have clear answers yet. And more broadly, there's the ongoing discussion about the wider impacts on human-machine interaction, beyond just tasks. Things like over-reliance on AI, the psychological effects of interacting with human-like machines. It's complex.
And speaking of profound impacts, let's talk about that provocative case study, the pregnancy robot.
Yeah.
This seems to push ethical boundaries to the absolute limit.
It certainly does. It raises fundamental questions about life, parenthood, and the role of technology in our most basic biological processes. The concept, coming from Chinese research, is to create a humanoid robot capable of carrying a pregnancy entirely within an artificial womb, from fertilization right through to birth.
Led by Dr. Zhang Qifeng at Kaiwa Technology, aiming for a prototype by 2026.
That's what the sources report. With an estimated cost around 100,000 yuan, about $11,000 or $14,000 USD, it blends AI, robotics, advanced bioengineering. It's incredibly ambitious.
How would the artificial womb part work? Hasn't that been explored before?
The basic concept isn't entirely new. It mimics a biological uterus, providing artificial amniotic fluid, nutrients, oxygen via tubes. Back in 2017, U.S. scientists kept premature lambs alive for weeks in similar biobags. What seems different here is the ambition for a fully automated process managed by the robot, from fertilization onwards, nurturing the fetus through the entire gestation.
Why pursue this? What's the driving force in China?
A major factor seems to be rising infertility rates there. They climbed significantly from under 12% in 2007 to 18% by 2020. For many couples, IVF doesn't work. So some supporters see this as a potential solution, offering hope to those struggling with infertility, or perhaps women who can't carry a pregnancy, or even those who wish to avoid the physical risks and demands of childbirth, a societal contribution in their view.
But the ethical concerns must be enormous.
They are significant, and our sources present them impartially. Critics raise alarms about fracturing maternal bonds, fundamentally distorting our understanding of parenthood, potentially commodifying reproduction.
Yeah.
Some feminist perspectives, like Andrea Dworkin's earlier warnings about artificial wombs, suggest it could even mark the end of women as a distinct biological category by removing their unique reproductive role.
Are there medical concerns too?
Yeah.
The social ones?
Yes. Some medical researchers worry that embracing artificial wombs widely could risk turning pregnancy into a kind of pathology, something to be engineered and managed, rather than a natural process to be experienced.
And the legal side. Science seems way ahead of the law here.
Absolutely. There's a huge legal and ethical void. Who counts as the parent? What rights does a robot-born child have? How do you prevent black markets in reproductive materials or these womb machines? Chinese authorities are reportedly considering policies, but these are global questions societies haven't answered.
So it's a real double-edged sword. Potential benefits for infertility or safer births, but massive risks, too.
That's the tension. Potential upsides easing pregnancy dangers, hope for families. Clear risks commodifying childbirth, undermining human bonds, shifting reproduction from people to machines. It's an incredibly complex ethical minefield that requires very careful consideration of the long-term human consequences, far beyond just whether the tech can be built.
A truly profound set of questions. Okay, looking forward then. What are the future perspectives? Where is this AI robotics integration heading?
The overall prediction is continued, accelerated integration, driven by ongoing advances in deep learning, reinforcement learning, maybe even new approaches like neuromorphic computing, brain-inspired chips. This will likely make robotic systems even more adaptive, intelligent, and autonomous, capable of tackling increasingly complex, unstructured problems that are beyond them today.
And collaboration will increase. More cobots.
Definitely. Cobots are expected to become even more common, moving beyond simple tasks, working more safely, more intuitively alongside humans, taking on more complex roles. It's about augmenting human capabilities, letting us focus on creativity and higher-level problem-solving.
What about the ultimate goal some talk about artificial general intelligence, AGI?
AGI is seen as the next major phase, achieving AI with human-like comprehension, learning, and adaptability across a wide range of tasks, not just narrow specializations. And for AGI to truly function in our world, physical embodiment robotics is seen as crucial. AGI needs mobility, rich sensory perception, touch, vision, hearing, the ability to interact physically with things in a nuanced way.
Why is the physical body so important for AGI?
Because it creates that vital feedback loop. When a robot acts in the world, it gets immediate sensory feedback, touch, sight, sound. This allows the AI to learn directly from real-world interaction, grounding its knowledge. It's how it builds understanding, similar to how a human child learns by exploring.
That's a fascinating point. The robot isn't just doing things for the AI, it's feeding the AI's learning process.
Exactly. There's a shift in emphasis highlighted in our sources. From just asking what robots can do for us to understanding the unique input a robot's interaction with the physical world can provide to the AI's cognitive development. Letting AI explore and experiment with tangible things could lead to a much deeper, more grounded level of comprehension. The robot becomes the AI's hands and eyes for learning about reality.
And this deeper integration, this learning through interaction, it will drive progress everywhere.
That's the anticipation. Substantial progress across manufacturing, healthcare, security, space exploration, everywhere.
Great.
The combination of AI's processing power and robots' physical skills could unlock unprecedented exploration and invention, bringing us closer perhaps to genuine AGI by letting AI learn from the richness of the physical world.
For that future to happen, what are the key development needs? Where does research need to focus?
For flying robots, a big one is extending flight time. That might mean novel, lightweight materials or structures, which also improve safety if there's a collision, and developing secure, intuitive ways for humans and drones to interact safely in shared airspace.
And for ground robots, like the ones in our homes or cities?
More research emphasis on safe, robust human-robot interaction is key, making that advanced capability more accessible, more affordable for widespread daily use, bringing lab-level safety and interaction into everyday devices.
And overall?
Overarching everything is the need for development methods that prioritize human-centered principles, and critically, maintaining the trustworthiness of these increasingly powerful AI systems, ensuring they align with human values, are transparent, reliable. That's absolutely essential for their acceptance and ensuring they truly benefit society, designing a future where tech serves humanity, not the other way around.
So let's wrap this up. What does this all mean for you listening right now?
Well, we've journeyed through this really intricate synergy of AI and robotics, from the basic definitions through the history, the amazing applications across so many industries. And we've also confronted the very real technical challenges and those profound ethical dilemmas like the pregnancy robot concept, which really highlight how science can outpace our societal readiness.
And understanding this intersection, it isn't just for the tech crowd, is it? It's crucial for anyone living in a world increasingly shaped by these intelligent machines. It's not just about what robots can do, but how they're enabling AI to learn and evolve, and what that means for all of us.
Exactly. And as we continue building systems capable of human-like understanding, maybe even simulating aspects of life itself, we face these huge questions. Questions that are likely to define this century. How will our definitions of intelligence or consciousness, or even what it means to be human, how might they evolve? And perhaps most importantly, what responsibilities do we have collectively as a society? How do we shape these incredibly powerful tools to ensure the future we build is not just technologically intelligent, but also equitable, humane, and truly aligned with our deepest shared values?